Okay, good evening, everyone. So this is going to be the lecture 5 for this course on applied differential geometry in mechanics. So in the previous class, let's just go through what we have uh, discussed so far in the previous class. So essentially, we set out to parameterize a surface, right? So yeah, we parameterized a surface and then went on to trying to understand the curvatures by making an analogy with curves, right? So we wanted to understand what are the curvatures, how do we measure curvatures of a surface. So one way is that in curves we could easily do it by looking at the turning rate of the tangent vectors. And then we could also show that not only the turning of angle, the turning of the tangent vectors can give us a measure of uh, curvature, but as well the same can be done even by using the normals, the turning rate of the normal vectors, right? So in surfaces, it's we have we use the methodology from the point of view of the change, right, in or the or the gradient of normals along the coordinate lines, so to speak, of a of a sphere, or more generally surface. And then we could construct what we call as uh, the second fundamental form, right? So L, M, and N is what are known as the coefficients of the second fundamental form. So using this, what we can have is that we get some idea about the curvatures. It does not mean that it gives us a true measure of the curvature. However, it does give what we call as the some sort of an idea of the curvatures, right? And we could see that for a flat surface, L, M, and the coefficients turn out to be equivalently right, equally zero, indicating that there is no curvature for a planar surface. Then we moved on to defining what we call as a Gauss map, which is just the mapping from a point on the surface to a normal vector, and which is the local normal at that point. And it lies on the tip of such normal vectors lie on the circumference or the boundary of a sphere. So the mapping is what we call as the Gauss map. Then we went on to understanding what we call as the Weingarten map, in which case what we would require is that the gradient or the differential of the normal, it lies in the tangent plane. We could show that it lies in the tangent plane to the point P of the surface S, right? And we could see that this tangent plane is the same as the tangent plane of the at the normal, at the tip of the normal, which which lies in the boundary of of a sphere, of a unit sphere, right? So we could show that we represented some sort of a mapping between the tangent plane of a surface to the tangent plane of the unit sphere, which eventually came out to be the tangent plane itself. Mm. So in the sense that the derivative of the Gauss map happens to be a linear map from the tangent plane of S to itself, right? And then the Weingarten map, as we recall, is just the negative of the Gauss map, right? And all it does is it will map vectors lying in the tangent plane at point P of the surface S to vectors in the same tangent plane. So in abstract form, this is how we represent, right? And being it linear, so it just means that it takes some vector operationally. If we look at it, takes some vector and maps it to the maps it to vector in the tangent plane itself. Fine. Now our now goal remains to represents to understand or essentially to represent the Weingarten map, right? So we started with a say a general vector which lies in the tangent plane, this W vector, and since it maps to the plane itself, to a vector in the plane itself, then let's have a general representative as delta sigma u plus gamma sigma v, and WP of S alpha sigma u plus beta sigma v. This is the what we call the expansion of W, or the representation of W vector in sigma u sigma v frame, or sigma u sigma v basis vector. And we then went on to look at some special cases. Now consider that W vector is sigma u vector, then it takes this WP, this shape operator, so to speak, of sigma u is minus d by du of the Gauss map at sigma u v naught. So for a constant coordinate line v is equal to v naught, we only are varying u, right? And differentiate it with respect to u and take its value at the point u naught v naught. So operationally, uh, it implies this WP S of sigma u vector. It implies that it gives us a change in sigma u along u coordinate, right? Likewise, WP S sigma v gives us a change of sigma v along v coordinate. And then we have this representation W of sigma u is equal to minus partial n by partial u. Likewise for sigma v, this is what we are given. So it means that we can clearly show that in general, we have this form, so to speak, right? W is equal to alpha nu vector minus beta nv vector. Now we would like to understand the curvatures. Right? So uh, let's define the Gaussian mean and principal curvatures. So Gaussian curvature is the determinant of the shape operator, and mean curvature is the average or the trace or half of the trace. It's the half of the trace of the shape operator. Right? Right? Now, our goal remains to represent. So our goal remains to represent the shape operator in some basis. And say in some basis the coefficients are A, B, C, D, or maybe I should just to be fine, just to be consistent. Let's put it like this. Let some basis let the coefficients of this be A, B, C, D. So in that case, the Gaussian curvature is just determinant of W, the matrix W. So it is AD minus BC, and H is the half of the trace of W, the matrix W again. This means it's A plus D by 2. And the principal curvatures are nothing but the eigenvalues of W, I should say matrix W. Right? And we also recall that the Gaussian curvature is an intrinsic curvature, which implies that it remains the same despite the change even in the orientation of the normal vector to the surface. Right? And the mean curvature remains as a it's called as an extrinsic curvature because it depends on the choice of n vector, which is the normal vector. So now we proceed to do the uh, what you call the most important part of this entire process is the representation of the shape operator itself in some basis. So we choose a basis sigma u sigma v because that is what defines the tangent plane. Right, the span of this defines the tangent plane. Right, and we know that w of sigma u is equal to minus nu, and w of sigma v is equal to minus nv. Right. Now minus nu is equal to a sigma u plus b sigma v, and then minus nv is equal to c sigma u plus d sigma v. Right? And taking dot product with sigma u, sigma v respectively, and others going through all this process, we get this four equations. Right? This maybe I should mark it first equation, second, third, and fourth. Right, and we have recall that A, B, C, D are the quantities which are unknown to us as of now. So we construct matrix equation using equations 1, 2, 3, and 4. And that's what we get. Right, and the EF FG forms the coefficients or this is a matrix which is constructed of or yeah, containing the coefficients of the first fundamental form, and LMMN is the symmetric matrix which consists of the components or the coefficients of the second fundamental form. Okay, and then we use the usual process of inverting the matrix F1, and this gives our ABCD matrix in terms of the coefficients of the first and the second fundamental forms. And using this, we could cleverly, in fact, it's very straightforward here. We're just determining the Gaussian curvature, which is determinant of this matrix, and the mean curvature, which is the trace of this matrix. Right? And the principal curvatures are nothing but the eigenvalues of A, B, C, D. Right? So this gives us our principal curvatures. And today we plan to uh, go further and talk about normal and geodesic curvatures and discuss further on the red theories. Or maybe we'll start red theories. So I will start, in fact, taking some inspiration from Team Healy and Professor Ajit Kumar's notes. Right. So here we would be setting out the basics or the fundamentals to be able to comprehend these theories, right? Okay, so let's begin our current this session. I mean the current lecture, which is lecture 5 here. So we would like to understand what are normal and normal and geodesic curvature. Beforehand, what are geodesics, right? So geodesics are essentially curves on a surface, curves embedded in a surface, are what we call as geodesics. And particularly, the goal is to understand what is the curvature of a curve which is embedded in a surface. That is what we aim at. Okay. So say we have a surface. Something along those lines. So we have a surface here, and this is a curve in the surface. And at any point, this is our tangent plane. So this is point P, this is our TPS, and this is the surface S. And this is some curve. This is a curve which is gamma vector, right? And at that point P, the normal to this will be the normal vector. This is the normal vector to the plane, tangent plane. and, and as we recall that the local tangent vector of this to the curve at point P would be given by this is the gamma vector and gamma vector dot, right? And we choose gamma vector has to be a unit speed curve. So here it so happens that gamma vector uh, of S is 1, right? The norm of this is 1, and gamma vector is perpendicular to the acceleration is perpendicular to gamma vector, and this we will have some arbitrary direction, say this. Right? It's just that it has to be 90 degrees. This gamma double dot vector, and we also know that the gamma vector and n vector and gamma vector dot lies in TPS, right? So which means that gamma vector dot is already perpendicular to n vector. So which means that we can construct a third vector, right? So we construct a third vector to form a triad, right? To form a triad of orthonormal vectors, right? It's just a set of orthonormal vectors. Since gamma vector is the norm is 1, n vector is of course has a norm 1. So what we'll do is we'll have a third vector which is gamma dot cross n vector, and which is going to be this gamma dot cross n, right? And you can clearly, okay, from the right-handed uh, rule, it should be right? So actually it so happens that we generally tend to write it in this fashion, and cross gamma vector dot. So in that case, this is the, of course, it varies from book to book, but we are specifically following Presley's book here. So all our conventions will, I'm just taking that as the base to for us, what do you call, choosing our conventions for the study. Right. So which means that we have a triad is n vector. So the n vector, gamma vector, and n cross gamma vector. These are tried. Right? Now we recall from the Frenes-Serre equation, from Frenes-Serre equations, we have is that gamma double dot is equal to kappa n vector right? So this kappa is what we call as the principal curvature of the curve, and n is the what we call principal normal to the curve, right? And this remind you that n vector is not the same as capital N vector, right? Need not be the same generally. It's only under some special cases that we have both these quantities to be equal, right? So now, since we know that since gamma double dot vector is perpendicular to gamma dot vector, this means that gamma double dot won't have, or gamma does not have any any component along gamma dot, right? So we can call that we have gamma double dot lies in the plane. Frankly, I mean, Precisely speaking, gamma double dot lies in the plane spanned by n vector and n cross gamma dot vector. This also gamma dot here, typo. So which means that we can have gamma double dot vector is equal to, let's have the, so we call this as say some kappa n vector plus kappa g n cross gamma dot vector. Fine. So this is what we mean here. Okay. Fine. So which means that kappa n is equal to gamma double dot n vector, and it is called as the normal curvature. So it's like the component of the curvature about n vector, and kappa g is equal to gamma double dot n cross gamma dot vector, and this is what we call as the geodesic curvature. Fine. So this is what we what we have as of now. I'll just mark both this. These are very important concepts or important quantities. Keep it this way. Fine. So now let's try to determine the expression for let's try to determine the expressions for. So one more thing what we have here is that we want to determine the value of principal curvature, kappa, right? So what we have here is, let's take a look. So we know that the norm of vector is independent, or maybe you can call that is invariant with respect to its uh, representation. Right? So what I mean to say that we have gamma double dot from Fresnel's equation as kappa n vector, and from here what we have is kappa n vector plus kappa g n cross gamma dot vector. So let's take it, its say inner product with itself. It's gamma double dot kappa square Yeah. And of course, this is nothing but just the norm squared of this, right? So likewise, the norm squared in this sense would be double dot dot gamma double dot, and we recall that n and n cross gamma vector are orthonormal, right? So which means that we'll have here as just kappa n squared plus kappa g squared. So this means that the principal curvature of the curve lying in the surface or the geodesic is equal to normal curvature squared plus the geodesic curvature squared. But there is also one such important property. Fine enough. Now let's try to obtain some sort of we will try to um, okay. So uh, the normal curvature is for a unit speed curve in, on a surface or on a surface S is given as so what we have is that kappa n is equal to n we already had n vector dot gamma double dot, and this we recall that it's the same as n dot gamma dot, right? And this seems to be a product of the Weingarten map of gamma dot vector gamma gamma. It's just the inner product of these two quantities, and which we recall from, of course we could not discuss this in class, but it is known to be equal to the inner product of gamma comma gamma dot. And this is not a very, it's a special inner product, right? It's defined with respect to the basis of uh, of the tangent plane itself. So it's not a normal inner product. It's not the usual that we know. It's a special case of inner product. It's like a specially constructed inner product, which is defined as So this is defined as, so for a general case, it's defined as for any two vectors uv, we define this as L duv vector duw vector plus 2m du of v vector dv of w vector plus n dv of v vector and dv of w vector. There is the specially constructed. Now for v vector, w vector is equal to gamma dot vector, right? So in this case, what we have is, say, the gamma dot lies in, say, gamma vector is defined in terms of sigma, or in terms of this patch as sigma of u comma u of t v of t, right? So gamma dot vector, I should say s here because this is we meant unit split curve, right? So we'll have sigma u, right, and then u dot of s plus sigma v dot, right? We use this chain rule here. So what we have is that du of gamma dot, this is a linear function. Du gives us the component along sigma u vector, right? So this gives us component of gamma vector t along sigma u, right? So this is nothing but just u dot. Likewise, dv of gamma vector dot is equal to component of gamma dot along sigma v. This is nothing but v dot, right? So which means that the specially constructed inner product is gamma. So this is given as L, L, M, N are the coefficients of the second fundamental form. L du and of v and this, so it's like u dot cross into u dot, so it's u dot square plus 2mn 2m du of v is u dot, dv of w is v dot plus n dv of v vector is u v dot and v of w is also v dot. So this is what we have as the kappa. Very, and what to know, what there is to, it's to note that kappa n depends on L, M, and N, right? Which again depends on the, so it depends on the deformation of the surface, right? Because due to deformation, sigma uu will change, right? Sigma vv will change, so which means that kappa n is an extrinsic curvature. It simply implies that since kappa n depends also on how the surface is deforming, that is the reason kappa n is an extrinsic curvature, right? Because it depends on the coefficients of the second fundamental form, which is very much closely related to how the surface is deforming, right? Now let's take a look at the uh, the geodesic curvature. So geodesic curvature is the geodesic curvature is defined for a unit speed curve on a surface sigma surface paths, of course, although we didn't discuss much about surface paths, but surface path sigma vector. Uh, and the curvature is thus unit curve is given as gamma vector of S is equal to sigma vector U of S V of S. Then with the surface patch with first fundamental form, E du squared plus 2F du dv plus G dv squared. Right. So for this case, the surface, the geodesic curvature is defined as V double dot U dot minus V dot U double dot EG minus F squared plus AU dot cubed plus BU dot squared V dot plus C U dot V dot squared plus D V dot cubed. Where A, B, C, and D are are expressed in terms of E, F, G, and their derivatives. So we recall one important thing that we note here is that Kg only depends on first fundamental form, but not on second fundamental form. Right? This is the important thing to note. So which means that if the deformation of a surface is isometric, which means that distance preserving, then kappa of G does not change. I mean, then first of all, then EFG doesn't change or do not change, right? And since it's isoperimetric, then even U dot V double dot, they also won't change, right? Like all of them, all of these quantities won't change. Neither would U double dot, V double dot. None of them changes because we are ensuring that the distance is remaining preserved, right? So which means that this simply implies that kappa G does not change. And this gives us a nice, so kappa G is an intrinsic curvature. Right, because it's very intrinsic to the surface. It does not change despite deformation, if provided that it's an isometric deformation, right? And this is a very important result which will be used to while modeling ribbons. So that is where we inextensible ribbons. So this kappa G being constant has a major role to play in the modeling of the energy function. Okay. Okay. So I think with this, we are all set to begin our study on our lectures on red theories. Rather, I would call it more specifically, let's call it rod mechanics or mechanics of elastic rods. Although we begin this mechanics of elastic rods, but let's go through some fundamental aspects of what we call as the elasticity, right? Let's review elasticity. Review the basics of elasticity. For the first, first of all, we should understand what is elasticity, right? So elasticity is the tendency of a structure, of a material or structure to return to its original configuration once the external stimulus is removed. So, figuratively speaking, we have some body, say, let's consider it to be something of this cuboid like body, right? To be for a bit more, let's have something like this. Right? And then we apply some sort of a force. And let this be deformable body as well. So let's apply some sort of a force like this and let this end be fixed. So after applying this force, it will assume this particular form. Say it say maybe slightly what you call exaggeration, but let this be the deformation as the force is being applied. You're just applying the force F, applying F. Right? Now, let's say that we are just applying, applying. And as we say remove this force, say we remove the force, then it will return to it becomes the same. It gets restored to its initial configuration, right? So figuratively speaking, I mean, we had this, then we applied at some time t is equal to 0. This is some t is equal to t final, some at some later time. Then we remove it, right? So it's like t greater than t final. Then it's returning back to its original state. So this is what elasticity means, right? Right? The body or the structure gets back to its original position. Now, then we go back and try to review some what we call as the Hooke's law. Of course, this was the simplest elastic model. So the idea was Hooke's law. So the idea was to find a relationship between the applied force and the deformation of the body. So let's consider some say bar, right? And we are applying a force F. It's simply speaking, we are pulling it on both sides. Then what happens is, so this was some original configuration L naught, let's call it L naught. Then after applying, this becomes slightly larger. So unless we have some right? So the distance of this is the length of this deformed is L. And we make some assumptions, so to speak, here. Of course, I did not explicitly, it seems that I didn't make that assumption very distinctively here. So it should be, let's consider of the same dimensions. Let the cross-sectional dimensions do not change. Right? So we make an assumption here that so this is under static equilibrium. So in this case, what happened is, at finally we'll have some extension L for the total length to be L. And in this situation, the internal restoring force is equal to external force. So in that situation, that's what we call as the static equilibrium. So in this case, even if you pull after some time, even if you are pulling with force F, the body does not stretch anymore. So which means to say that right? So what happens is we have change in length. So originally the cross section area was say A, and this A is like A naught, let this be A, and we assume A naught is almost equal to A. So like there is very negligible difference. That is just an assumption. Yeah. Although in reality it does change, but let's just for the moment take that. So now let's look at the change in length. So change in length is delta L, and this is nothing but L minus L naught. And then using this, we define something called a strain. And strain is epsilon, and this is given by the change in length with respect to the original length L naught. Right? So this is what strain is. So as per Hooke's law, and before that, let's also define something called as a stress. Now stress is equal to the internal resistance to the external force. So in general, what happens is, the way we define stress is always force divided by, since at the time of internal resisting force becomes equal to the external force. However, a stress here is always internal resistance per unit area. That's what we call is per unit area. So we want to look at the overall, so to speak, in a distributed sense. That is what stress is. So in this case, at equilibrium, what we know is just F internal is equal to F external, right? So in this case, it will be F internal divided by A naught. And this is the same as, of course, it should be A, but since we have already assumed that A is not equal, is almost equal to A, so it's just A naught. Then we'll have F by, and this we call as sigma. Now, as per Hooke's law, or according to Hooke's law, sigma is proportional to epsilon. And this implies that sigma is equal to some proportionality constant, we call it capital E into epsilon. So E is the proportionality constant. Proportionality constant also, and E is often called as the Young's modulus. And here we have a assumption again that this epsilon must be much smaller than 1. It's because this is a ratio, so epsilon is a non-dimensional number. It's length by length, so lengths, the units cancel out. So we have just it's a non-dimensional number, and it should be have a value which is much smaller than 1. Fine. So according to Hooke's law, that's what we have, sigma is equal to E epsilon. And finally, we can write as F by A is equal to E epsilon. This implies that F is equal to E A epsilon. So far, so good, right? We could, this is from Hooke's law when we are applying a longitudinal strain. And maybe I should write it in, because Hooke's law is the bedrock of what we are doing today. So I should probably highlight it. It's called Hooke's law. Right? And this was for a linear stretch, right? In other scenarios, we also have this in different such scenarios. One is what, say we have what we call as the say we have this body, Let this side be fixed to some wall. And then we are applying some sort of a bending, what we call M, right? And this is, of course, I'm giving a side look, but I mean, slightly just to expose the cross sections. Now, if we look at properly from a side, then this is how it would look. Right? So there's a cross section. Now we are applying moment M. So in this case, because of the application of this moment, it deforms, right? It deforms into some sort of a something along these lines. Right? Which means that it induces some sort of a curvature, kappa. Of course, I'm like some sort of a curvature, which means it's changing from theta direction, theta angle with the respect to this horizontal axis. So overall, this is creating some sort of a rate of twist or rate of that again, as we learned. So we have the center line of this, say line which is passing through the centroid of every cross section. So centroid is the, of course, it's a mathematically, what do you call? For a circular cross section, the centroid is the same as the center of the cross section, right? So it's a locus of this, and this, so this they can be modeled as some sort of a curve, right? This is a curve. Now, this makes an angle, the local tangent vector makes an angle theta, and then the m, I mean, the rate of change of theta with respect to the arc length coordinate, right? So it's so from here to here, it's L, let's call it L. And at any point, it is the distance is S, right? So, so it's like we have S from here to here, and till here we have of the center line will be S is equal to L naught, or let's call it L naught itself, not no worry. So here we have M is proportional to kappa, and kappa is curvature, which is d theta by ds, and this is called curvature, as we recall from our rod theory. And the proportionality constant is what we call as EI into kappa. E is Young's modulus. I is what we call as the area moment of inertia. So for a circular cross, it varies from cross section. So this I is a property of a cross section. Is a cross sectional property. Right? So this M is equal to EIK, EI kappa is what we call as the linear bending law. Of course, I'm not going to the very fundamentals of how it's derived, just for the sake of brevity, right, of these lectures. I'm not going to derive. We can easily derive what this quantity is I and all, but just for the sake, I'm keeping to a basic minimum, to a bare minimum, so that we are able to follow what we are trying to discuss in this, what we aim at achieving in this lecture series, right? So this was bending. Now there is another scenario, and I'll take this figure here. I'll just copy it and paste it here. So bending was it was like we are applying in a way of say perpendicular to the, in that sense, right? We are applying in a perpendicular to the cross section. I mean, loosely speaking. Then the third part is what we call as the torsion. So considering this to be the axis, which is passing through all the centroids, then we take a torsion, which is like twisting the cross section. It's like applying a couple to the cross section with some with what we call as the T. So it is T is the torsion. T is the torsion. And M here is the bending moment. I did not specify clearly, but it's bending moment. Now, in this scenario, as we are twisting, then say initially we had uh, one such vector, say this here. And initially, this vector was, let's have this vector throughout the cross section and let it be parallel to the vertical direction, which is say E3 or maybe E1. And let E3 be the axis and E2 be the one other vector which is spanning the cross section. So along E3 is our axis. So this is our E3. Now, the vector along E1 is constant throughout uh, before we are applying torsion. However, after this, what happens is this structure twists. I'll just paste it here. So the vector on towards the base is the same. However, as we move away from the base, this seems to be rotating. And eventually we'll have that some rotation here. Of course, I made some very drastic. Let's not be as drastic here. This just to show that it's rotating such that it will be like this here now. So initially it was parallel to E1. Now it will not be parallel to E1. It is making some angle, some say phi. Of course, this phi is an angle which is throughout. It makes after deformation at every angle. So angle between, so we have at S, angle between this vector here, A vector, let's call this as A vector. Right. So this A vector with respect to E1. So the angle between between A vector and E1 is called phi, right? As we are applying this torsion. Right. So then we have something called as a twist. So twist is called as say tau. So we are applying, ideally we call it not torsion, rather we call this as torque. And this twist or torsion is the quantity here that is given as d phi by ds. Now we have a relation between torque and twist. And again, T is directly proportional to tau. And then we can have as T is equal to the proportionality constant being G, J, tau. Now G is what we call as the shear modulus. Mind you that this is shear modulus only for a circular cross section. That's assumed, right? And then J is what we call as the polar moment of inertia. And this is again one third type of, it's also a linear law for torsion. That's loosely what we can say, right? Fine. So we have three different for a beam. Right? So for this it was bar, but beam is a general case, right? So beam a bar can only take extensional loads, so loads along its longitudinal axis, but bar can take transverse loads as well, right? So that's the reason we are considering as bar or beam. So sorry, this we call as them as beams. So they're all beams. Fine. So with this, what happens is, so our goal was to study something along a line of we just wanted to study some basics of elasticity, and this is what basics of elasticity mean. In all cases considered so far, in all the above cases, epsilon, kappa, and tau is very small. It is very small, just for the bending law to hold. However, it does not mean that I mean they have to be same, but still they can go large deformation. Recall that epsilon, kappa, and tau are just measure of the what do you call the change. Right? It just gives us an idea about the change. It does not. It does not, or what do you call it, the strength. It does not mean that we want it to be uh, like that the body cannot undergo large deformations. It can go. Body can still undergo large deformations, but even then, we can have epsilon, kappa, and tau to be much less than 1. So this is what we call here as the uh, the three, uh, so to speak, the three some sort of a simple deformations of beams. So that's what I meant to say here. So we are looking at simple deformation of beams. Simple deformation of beams. Now we can go much farther than this. Right? So let's try to get some idea about the Euler-Bernoulli beam theory. This is a very widely used, widely known beam theories. Let me just have a brief beam theories. So one such special case is what we call as the Euler-Bernoulli beam theory. In this case, what we have is we have this, say, E1, right? So ideally we can have X and Y, but I'll try to be consistent throughout. So let's call it as Z axis, and this has the Y axis. So that we are consistent with what we'll be following later. So this Z axis is the same as E3, and this to be E2, rather than or, because so as not to confuse with a scalar to a vector, right? So say in this case we have some sort of a curve in this scenario. Let's have some, of course, some beam, some planar beam. But as we recall that we can model the center line or the locus passing through the centroids of every cross section. This can be modeled as a curve. So in this case, it's a planar curve. Right? So this planar curve makes an angle theta with respect to the E3 axis. Right? So in this case, so theta is angle between Let this be the curvature t vector. T vector of z with respect to or with E3 vector, right? So now we can, based on this, we can have this, define this curvature. Curvature in terms of z at every location z, we can write it as d square y by dz square divided by 1 by dy by dz whole square to the power 3 by 2. Right? So far, so good. And for small, again, kappa z is equal to, so says for small dy by dz, so kappa z will be just d square y by dz square. There's 4. Done. Now the bending moment so here I must attribute that I am following materials by of notes by Professor Ajit Kumar of IIT Delhi. Right? Just to put things in perspective, I'm mainly basing my lectures on his notes on elastic welds, right? Okay, so bending moment kappa z, bending moment is m of z is equal to ei kappa of z. Right? And this is nothing but just ei d square y by dz square. And this is what we call as the Euler-Bernoulli beam equation. Euler-Bernoulli beam equation. So this is the most fundamental. So I'll just write it once more. So this is what we call as the Euler-Bernoulli beam equation. Fine. So of course, so we need to prescribe m as a function of z, and also boundary conditions, since this is an ODE problem at y is equal to 0 and y is equal, sorry, at z is equal to 0 and z is equal to L naught. Right? This we provide some some boundary conditions, then we can solve such problem. So this is what is roughly what we call as Euler-Bernoulli beam equation or beam theory. Now let's move to talking about what we call as the Timoshenko beam theory. So here there was a major assumption. So I forgot to mention the assumption. The assumption is that, and there is a very fundamental assumption in Bernoulli beam theory, which is that assumption is that say you have a beam and there is the center line, and this cross section will be perpendicular to the center line, and this is before deformation, and after deformation, so this segment, right, this linear segment would bend say in some form, right? And you have the center line. Recall that the length of the center line is not allowed to change. Generally speaking, we keep it constant. And that's the reason we call as that the central line or also it's called as the neutral axis. That does not go any tension or extension, tension or compression, right? So the central line, the cross section of the same point with this, and it will still remain perpendicular. So I should say before deformation, after deformation, or maybe it's like deformed, right? It still remains perpendicular. So the assumption is that normal sections to the center line remain normal after deformation. So I better call it after deform, although it's just meant to show that deformation has taken place. So that is the assumption, and this assumption is also called as Kirchhoff's hypothesis. Right? Now, what if we relax this assumption? So in Timoshenko beam theory, we relax this assumption. So relax the assumption. So it does not mean that we are fully abandoning the assumption. It's just that we are making some mild relaxation in the assumption. So the assumption is that, so the relaxation was that normal sections are still normal. So normal, right? Normal sections are still planar, but not normal in the central after deformation. So it means that this linear, so to speak, from the side, it looks like a line, right? The cross section still looks like a line, but it no longer makes a 90-degree with respect to the central line. Post deformation. No? That's what we can. This is what the relaxation essentially goes, right? So, so in that case, what happens is, now we had this cross section. It was making some sort of an, sorry, it was making a 90 degrees, pi by 2, right? Now after deformation, it so happens that, let this be the, so it's the normal is like that. The center line has deformed. And so the tangent to the normal was like that, or normal to the cross section was like this. Now it's stayed like this, but this is the tangent to the center line. So this gamma is some sort of a shear strain. So this gamma gives us, tells us about, so ideally I should also rotate it so that it does make some change. Right? So this was the tangent. This is the tangent you can clearly see, and this is the normal. There is an angle between both of them, between both this tangent vector and normal to the center line, and this is some say theta. So gamma is equal to, and the tangent makes an angle, the tangent to the center line makes an angle dy by dx, right? This is the dy by dx. Of course, it's not exactly the angle, but say in some small angles, we are all dealing with small angles here. So this is like dy by not dz, dx, it should be dz because this is the E3 axis minus theta. And this we can write it as t by k, t by g. So, or maybe tau by g. And I believe I had used tau somewhere else as well. So here the tau was torsion, but again, this is like shear stress. So let's call it as I think I should call it something else. Um, Here tau is shear stress. It's again some shearing force divided by tangent and be divided by the surface. So the way we define shear stress is you have this body, you have this surface with area A, and you're applying a force F. Right? It's a shearing force. It's like applied fully on the surface. So here this is given as F by A. Just to give you an idea. Right? So because of this, and then we can write it as V by V is the shearing force, K, let's call it V itself, why not? K G A. So V is the shearing force and K is the correction factor, or sometimes also called it shear correction factor. Right? Okay. Now, and A is the cross-sectional area. A is the cross-sectional area. So A is equal to cross-section area. Fine. So with this, what we have is we can clearly write dy by dz is equal to gamma plus theta. Right? So gamma is because of shear, due to shear, and theta is due to bending. Right? So with this, we have two sets of equations. Dy by dz is equal to gamma plus theta that we already have, and gamma is nothing but v divided by kga plus theta of z is also of z. And then we have ei. And now we are looking at the uh, how much the cross section is deforming. So cross section is like d theta by dx, right? This is equal to, so theta is the angle made by the cross section, the normal to the cross section with respect to the x-axis, or oh, sorry, with respect to the z-axis. So we are looking at how much the rate of change of that, or the turning rate of the cross section due to the motion, due to this application of the bending momentum. So this is what we have. And as we recall that uh, for no shear, or if no shear, if there is no shear, so this is what is Timoshenko beam theory, right? If there is no shear, then theta of z or maybe gamma is equal to 0. This means that dy by dz is same as theta of z. And this, so it means that the second equation is just ei. D theta of dz is just like d of dy by dz, right? So it's like dy by second derivative of equals z. And sorry, it should be, we just should be z here. This two as well. Right? So we have recovered, this is the Euler-Bernoulli beam theory, right? EP theory. Okay, so far so good. But now what we do is let's move forward and try to develop some simple functionals. So we have already understood loosely beam and red theory, right? I mean the beam theory. Now let's try to get to know what is called as strain energy. So you recall that as you're applying F, or maybe as we recall from Hooke's law, what we have is sigma is proportional to strain, and then we recall that sigma is equal to E epsilon, right? And then we know that as epsilon is increasing, even sigma is increasing, right? Linearly. So what we have is from the graph. So this is sigma, this is epsilon, and we make a graph. Say this is our graph, because at sigma is equal to 0, sorry, epsilon is equal to 0, sigma is equal to also 0. So it should pass through the origin here. There is 0. And say we provide, take it to some strain, say till here, right? Say this is some epsilon f final. So corresponding to this is the sigma final, right? So as we are say stretching it, or along, I mean, applying an extension load to it, to take to this point, we are storing some energy in the system, right? We're actually storing energy in the system. And as we recall here, that from the graph, we can clearly see that d epsilon by d sigma by d epsilon is just E, right? So there's the slope that is E. It's a fixed number, E, or the Young's modulus here. Now, what we want to know is, can we integrate it? Now, we integrate. At first, let's find the energy. To get the energy, say we have, I'll just remove this, all this patchwork, right? Or hatchwork here. Let's consider some level sigma. Let's look at some, of course, mathematically speaking, we are looking at some sigma here, and there's some from this epsilon, some sigma here combination. Then we are making a small stretch from this point, little extension from here, right? So that what we have here is we have some sort of a sigma is there, and then we make d epsilon is the small, say, like this is, of course, I mean, I think it would be better to put this in terms of work, right? Or say Of course, let's put it in terms of work here. So work done to do this is some say F into dx. And F, we recall, was sigma into A. And so I should call it dl. Just to, again, I should make the notation clear. So this was L naught of some body we're stretching with F, or maybe stretching on both sides. Maybe let's keep it fixed at one side. Let's stretch it. And as we're stretching, then this gets slightly elongated, right? So this makes sense. So this is like dl, right? So F into dl. This F, as we recall, is d sigma into A dot. dl was what we call as epsilon. D epsilon is equal to dl by L naught. And this one was just dl by L naught, right? And then what we have is sigma of A. Sigma is again, okay, so this is dl, right? So dl becomes L naught into d epsilon, and sigma is E epsilon. And mind you, there is a small work, right? A small increment. So E epsilon A L naught d epsilon. And this we can write it as E A L naught into epsilon into d epsilon. Now what we do is we integrate. We integrate from sigma is equal to 0 to sigma is equal, epsilon is equal to epsilon F. So which means that W taken from 0 to epsilon F of this entire quantity is E A L naught epsilon d epsilon is equal to E A L naught epsilon squared by 2, isn't it? And epsilon F squared, because after integrating, this is what we find it. And this we can write it as E A L naught. We can likewise write it as E epsilon F squared by 2 into A into L. And A into L naught is what is as the volume of the, let's speak, beam. And this is what we call as the stored energy functional, right? So W, oftentimes I should maybe, for a better convention, so as to not, let's just call it as U. So this was the U. This is the stored energy function, stored energy in the beam. And this simply implies that what we have is so U is equal to this quantity is called as elastic strain density or strain energy density. Now for L naught very small, or even likewise we would not have to do that, but even prior to integration we had that uh, okay, I think say for very of as L naught becomes very small, then we can have as L naught will be tending to some dx, right? And because of which even U becomes some sort of a du. So in that case you'll have du by dx, or maybe I should call as the L tends to delta x, this as delta u. So this one you'll have as delta u divided by a into delta x, right? This is equal to E epsilon f squared by 2. And now we can even relax it to be to some generic f. Like this should be some generic epsilon. Like let's take at any point till some strain level epsilon. Then what happens is limit delta x tends to 0. You can write it as delta u by a delta x as du by dv. Now v is volume element. So delta v is the volume element. This was just a delta x. And this you can write it as epsilon. And this is how you redefine strain energy function, strain energy density for a small element, right? And likewise, so this is a very important quantity. So let's call it as this is like uh, it's a very important quantity. I should just put it in something of this sort. Now, and since this is of course to close this argument, uh, say for beams of uniform cross-sectional area. So this was like a volumetric energy, elastic energy density, or volumetric strain energy density. And for beam of uniform cross-sectional area, A, then we can write it as, why not take it as du by A, and this will be dz. I should have used, but anyway, okay, let's, for the time being, let's just call it as x, no problem. Right? This will be equal to E epsilon squared by 2, and you can write it as du by dx is equal to EA epsilon squared by 2. And this is what we call as the linear strain energy density. So far, so good. Right? And from a similar argument, linear strain energy density, say for moment, for bending moment, in that case, we have it as EI kappa squared by 2. So kappa is the curvature, and for torque, right? Then we have GJ tau squared. This is just the linear strain energy density. And we can also prove it just by saying whether, let's look at the dimensions. So E has Newton per meter squared, and I has meter to the power 4, and kappa has per meter, right? So it's like Newton per meter square into meter to the power 4. So let me write it properly. So Newton per meter square, meter to the power 4 into 1 by meter squared. So this cancels out, so it's Newton, and Newton is like Newton meter per meter, right? You can clearly see that it's like energy, which is Newton meter divided by meter. So we have just verified whether the units are fine or not, or dimensionally consistent. So I think this is what we were aiming at. So what we can say is that for any beam of say length L or length L naught, or maybe why not capital L, so that later capital L or small l, anything, right? You can always remind the total energy. So total energy is always going to be the integral from 0 to L of strain linear elastic strain density into d of S. So I'm just introducing this S because this is what we are going to do later. So we'll be looking at arc length coordinate and element along the arc length. So this is what the general, very basic, very overview of what it would look like. So in the next class, we would be looking at we'll be looking at Kozrat rod theory. And of course, the special case, which is called as Kirchhoff rod theory, followed by ribbons, mechanics of ribbons in short. Okay, so with this, I'll be closing today's session. Let's meet in the next session. Bye.